My name is Matt Repasky, and in this video, Alexander Bukharin and I will discuss our approach and progress in developing a music genre classifier. First, I will describe the problem we are solving, our motivations in doing this project, and the applicability of the model. Then, I will describe the data acquisition through our use of a web crawler. Next, I will describe our choice for the initial representation of the data, and finally, I will talk about initial trials at building a model. After this, Alex will describe better ways to use our data, such as more complex and less sparse representations. He will then talk about our implementation of more expressive models, such as our implementation of neural networks. Alex will finish by discussing improvements that can be made for the future. Our goal in this project is to classify individual songs into separate genres. This is motivated by the tendency of popular music streaming services such as Spotify and Apple Music to attempt to cater to the tastes of their listeners. Our approach is similar to a natural language processing approach. We aim to take in the lyrics of a song and return its genre. This technique could be useful as a preliminary step in the music catering process, as we provide superficial categorization. In other words, we want to train a function mapping a song to a discrete genre in a predetermined list of genres. This is the classic structure for a classification problem, as we need to create decision boundaries in the feature space of our songs. The first step in solving this problem is finding a source for our song and genre information. Next, we must decide which is the best way to separate these songs into genres. Then, we will find a way to represent individual songs. Once the data is fully processed, the final step is to decide upon a model and a method to train this model. We decided that Genius.com would be the best source for our data, as the website divides its lyrics into 5 charts corresponding to 5 genres: pop, country, R&B, rock, and rap, which will become our 5 labels. In order to acquire this data, we utilized Scrapy 2.0, a web crawling module for use in Python. Scrapy's web crawling capabilities allow us to search through each of the genre charts on Genius, identifying the lyric pages for each of the songs in these charts. Once a lyric page for a song was found, Scrapy's web scraping capabilities allowed us to identify where in the page source the lyrics were located. Using this technique, we searched through the first 50 pages in each of the genre charts, resulting in 1,000 songs per genre. For each of the 5 genre charts, a text file was output that contained all the lyrics for every song in that genre. Each song in these files was separated by a delimiter, so we could later use each song individually. For our first text representation method, we decided upon the bag of words, a sparse representation method. The first step in representing our words is to clean up our data. For example, we needed to remove the punctuation from our lyrics and make every word be all uppercase. Once this was done, individual words could be obtained by separating each line into a list of words separated by spaces. Before we could represent our songs as bag of word vectors, we needed to develop a vocabulary across all of our music. To do this, we iterated through each song in all of our genres and counted every word, adding every new word to the vocab list. Once this was done, any word with more than 4 appearances in the music was kept. Then, we picked the first 800 songs in each genre, which are separated by the previously mentioned delimiter, and represented them as a vector that counted each word in the vocabulary as it appears in the song. This vector representation took the form of a NumPy array, a data structure provided by the Python module NumPy. Finally, a NumPy data file was created with 4,000 songs in 2 columns, each row being a labeled song vector. Using this vocabulary, we used the held.data to create a testing file in the same way, which consisted of approximately 1,000 songs. Now that we had a data representation for our songs, we could begin to develop our models. Our first attempt was in using a logistic regression model, utilizing the sigmoid function and softmax function, to predict the label of new songs. The sigmoid function acts to transform the linear combination of the features into a point between 0 and 1, distinguishing between 2 labels. The softmax function acts similarly, but works for a non-binary label. In our case, this is applicable as we have 5 labels. We used stochastic gradient descent to train the parameters and optimize the model, which was necessary as opposed to batch gradient descent since our dataset is so large. Both the model and the learning for this model were programmed in Python, primarily utilizing the NumPy module. Once trained, we tested the model against the approximately 1,000 songs in our testing data. We found that the accuracy of this model peaked at about 20%, indicating that this was not an effective model. Our second attempt was in using the naive Bayes classifier, which utilizes Bayes' rule in calculating the probability of particular labels. In using the naive Bayes classifier, the naive Bayes assumption applies, which states that all features are conditionally independent given genre, which is a very difficult assumption to make considering the size of our data. Our training method learned the posterior probabilities of each word given genre, but the prior could be ignored due to the fact that there is an equal number of each genre in the training data. This model was again produced utilizing NumPy in Python. Once trained, we found that the model was about 37% accurate on our testing data, again indicating that this model is not sufficient. The failure of the logistic regression in naive Bayes models is not surprising, as these are both linear classifiers. It is not safe to assume that our data is linearly separable, so a linear classifier is bound to have very low accuracy. In addition, this representation of our data is very sparse and inefficient. Our feature space consisted of 10,500 features, many of which are not likely important in the separation between genre. The bag of words method does not do anything to capture semantics of data either. As a result, our classifiers should not be effective in determining genre. These results showed us that we needed to improve the way we represented our data and switch to using more expressive models.
Okay, so previously we had been using the bag of word representation, but the problem with this is that our data had a really large dimension of 10,000, and this would make all of our classifiers need a lot of memory and take a lot of time and be really complex. So instead, we used principal component analysis to reduce the dimension to 40. 40 was found just by looking at the eigenvalues and seeing which ones were significant, and after 40, they were all close to 0. Then, with this newly reduced data, we implemented a multi-layer perceptron. So this was only with one hidden layer and 256 units with ReLU activation. And this achieved an accuracy of around 30%. And we think that we can probably make this higher in the future with more hidden layers and maybe wider layers as well. Okay, but we still thought that there's lots of problems besides the huge dimension with the bag of words model. Like it doesn't really capture the meaning of words. So the word to vec, we use the word to vec method to transform each song into a sequence of word vectors. So each word in the song is turned into a vector, and then a song is a sequence of words, so it becomes a sequence of vectors. And then to ensure that each song had the same length, we use zero padding. So like if the maximum length is 8,000, around 8,000, if a song has only a length of 5,000, then we append like 3,000 vectors of just zeros to the end of each list. But the problem with this is this resulted in a really large tensor with size 8,000 by 300 for every song, where 300 is the dimension of each word vector. So our goal was to implement an LSTM on top of this. An LSTM is a recurrent neural network architecture that can capture long-term dependencies, where sometimes a normal recurrent neural network would not capture this. But because, as we mentioned in the previous slide, the dimension of the data was so big for each song, it's 8,000 by 300, we only actually used the first 100 words of each song. And this helped, make our neural network a lot less complex and take a lot less time to train. And so this again had a similar structure to the multi-layer perceptron, except that it's a recurrent neural network, but it has one layer. And with this, we are able to achieve accuracy of 47%. And again, we think that by adding more layers, we can probably achieve better accuracy, and by training it for longer. Okay, so even though we implemented all these methods, we think there's still a lot of ways that we can improve our classification methods. So by increasing the depth and the width of the neural networks, like I mentioned before, this can allow our neural networks to capture more dependencies between words. And then also by increasing the size of the data set. Right now we scraped 5,000 songs, 1,000 songs from each genre, and then we train on 4,000 songs, so then we can cross-validate on the other 1,000. But instead, we might achieve greater accuracy if we say get 10,000 songs. So that's something we can work on. And then an additional step that we can take is for the LSTM is to make it bigger and keep track of not only the first 100 words of each song, but maybe like the first 1,000. And that's it.